You're welcome to day 17 of 50 days of tutelage. In today's class, we're going to be learning about projectile motion. And I foresee that this class is going to be longer than the usual classes that we've always had. So get your pen and your paper and pay attention to every single thing I'm going to be discussing in this video. If you have been struggling with projectile motion, this is your opportunity to lock in. Just lock in, and I can promise you by the end of this video, you're going to understand every single thing about projectile motion. So let's get right into it. Before we proceed, I remember in our previous class when I was talking about, that was 2 classes ago, I spoke about the equations of uniformly accelerated motion, and I said we also call it the Suvat equation. So if you remember, we had the likes of displacement equals u plus v divided by 2 multiplied by t. That is displacement is s, and u is initial velocity, v is final velocity. Then we also had another one that says that v squared equals u squared plus 2as. I'm just trying to list them out. We have v equals u plus at, and then we have the one that is s equals ut plus half at squared. So we have these 4 equations of uniformly accelerated motion, and I'm going to be going from there. I'm going to be talking about a lot of things about projectile motion going from this equation, because these equations kind of also find their way into that space as well. Now, I'm going to be changing the dimension of these things now. I'm going to be talking about upward and downward movement. So whenever an object is thrown upward at a certain velocity, or the object is made to fall freely from a certain height downward. Now, these objects also they undergo uniformly accelerated motion. In this case, that uniformly accelerated motion is acceleration due to gravity. Now, take note that in generally we regard gravity as a downward acceleration, so therefore it's always negative. But for the context of for the narrowing it down to how I'm going to be taking this class, I'm not going to be using it as a positive entity or a negative entity. I'm going to be changing it based on different directions. So just take note of that. Now, a lot of things will change in this situation. Now, our displacement, we are talking about this displacement based on horizontal motion. Now, in this vertical motion of going up and going down, so we're going to be talking about it as height. So the displacement is going to be regarded to as the height. So A is becoming G and S is becoming height. So the initial velocity and final velocity, they remain the same. So let's do some analysis and see what happens when you throw an object up. So the first thing is that before you can throw an object up, you must actually give it an initial speed. That is why we had discussed about force, force being the agent that causes motion to happen. So when you impress force on a body, what is going to happen is that you are giving it a certain speed. So if this is the object and you want to launch it upward, it is going to be launched upward with an initial amount of speed. So in this case, we say it has initial velocity u. But if that is the only thing that you did to the body, you are not continuously supporting the body as it is going up. Then what happened is that this initial velocity that you had given it, it gets to a point whereby it is going to finish. Because the initial velocity, the moment it takes off from the point of launch, the initial velocity that you had given it begin to decrease, begin to reduce. And so at the point, it is totally exhausted, and you no longer have that speed to continue to move up again. So by the way, an object would stop moving if that been projected, or if that been impressed by a force to start moving. An object will stop moving on these 2 occasions. Number one, if they had exhausted their initial velocity, or number 2, if they hit a barrier. So if an object will stop moving if it has exhausted its initial velocity, or if it hits barrier. So what I'm trying to say is that upon the impression of force on any object, it gains a certain velocity, and this velocity at a particular point in time it begins to decrease, and it decreases through retardation, and the body goes to rest, will stop moving. At that point, it has exhausted its initial velocity. Or if it has not exhausted its initial velocity, it hits a barrier, and the barrier tends to absorb the motion, then the body is going to stop as well. So back to this now. If you throw an object up, you know that at a point in time, the initial velocity is going to diminish and the body will stop. Let's say it stop arbitrarily in the air for, like, let's say, a few seconds. Now, that point where it stops, we say it has reached its maximum height. So what should you note like that? At that point, there's a momentary stop. So it has a final velocity there. That final velocity is going to be 0 meters per second. Why? Because the initial velocity in this case is going to be maximum. As it is going up, the initial velocity is reducing. The velocity is reducing until it reaches the maximum height, and therefore having a final velocity which is 0. But on the other hand, if you allow an object to drop, you did not throw it down, you just allow it to drop and fall freely. In this situation, the initial velocity is going to be 0 because you just dropped it. You did not impress a force on it. But as it is going down, it begins to increase in velocity. It increases in velocity until it reaches a point just before reaching the ground, where it has its final velocity to be maximum. So you can see the difference between the two now. So what can you now see now about when you are going up and when you are coming down? So if your speed is decreasing as you are going up, like I've explained in the previous class, that means that you are experiencing a retardation. And if your velocity is increasing as you are coming down, that means that you are experiencing a form of acceleration. So since the acceleration in this case, like I said, for upward and downward movement, vertical movement that are done in this manner, no special impression than the one I've explained in this case, no special impression of forces, then the acceleration in question is the acceleration due to gravity. And so since going up is a form of retardation, so the acceleration is going to be negative g. In the case of coming down, it is accelerating actually, it is increasing its velocity, so the acceleration is going to be a positive g in this situation. Like I said, g is always regarded as a negative thing, but for the purpose of the context of how I'm going to be teaching you everything now, I'm going to be using directional way to define g, to define the sign of g. Anyways, it is still going to give you the same exact result, even if you use the general notion that g is always negative. But I don't want to go into that because that might be a little bit confusing. So let's get into it now. So we can fine-tune each of these equations of motion now. So for the first one, we can say now that h equals u plus v over 2 multiplied by t. So the only thing that's changed here is h. So in the case of v squared equals to u squared plus 2as, if the body is going up, like we have said, that's a retardation. So we have v squared equals u squared minus 2gh. So a changes to g, a changes to negative g, and s changes to h. If the body is going down, it is v squared equals u squared plus 2gh. If the body is going down, it is v squared equals u squared plus 2gh. The next one is s equals ut plus half at squared. So it becomes h equals ut minus half at. So it's not going to be a now. It's going to be minus half gt squared. This is when the body is going up. And it's going to be h equals ut plus half gt squared. This is when the body is going down. So this is for up and this is for down. And the last one there, we have v equals u plus at. So we're going to have v equals u minus gt when it is going up. And we're going to have v equals u plus gt when it is going down. So take note of this for anything that is describing the motion. Oh, sorry, my notes, I think I jumped from page 1 to the last page. So that's it for upward and downward movement. Now, let's get into projectile proper. So what does it mean to actually project a body? Projecting a body is not really anything special. In fact, it is definitely, you can say projectile motion is just the launching of an object into the air. Like you're just throwing it up. That's just what you are doing. So which makes the question that there is a field of throw for a projectile that is being launched, and the field of throw is contained in this region. That means that you can decide to launch it this way, you can decide to launch it this way, you can decide to launch it at any instance here. So as long as there's a sense of it following a form of parabolic movement, then it's a projectile motion. So this region is actually a field of throw of any projectile motion. So that is why what we're going to be doing now, so we're just going to be picking an arbitrary one. So let's say, for instance, you launch a projectile. So let's make this is the x-axis, this is the y-axis. So you launch a projectile. Of course, if you throw a projectile like this, what is going to happen is that the body is going to take a parabolic movement of this nature. So let's say this is the body, assuming it is a ball. Let me pull that right here. So the body is going to take this parabolic path. Yeah. So this is a projectile motion. But because we don't know too much of a calculus yet, we cannot analyze the motion as the parabolic form. So we tend to draw a linear tangent to the graph. And this linear tangent represents the u, the initial velocity with which it was thrown. And this initial velocity is at an angle theta, So that implies that this motion, the projectile motion, is a motion that is done in two directions. We have the x direction and we have the y direction, or horizontal direction and vertical direction. So projectile motion is to be studied using two-dimensional analysis. That is the horizontal component and the vertical component. So there's a component of the there's a component of the velocity which is in the horizontal, and there's a component of the velocity which is in the vertical as well. You need to be able to analyze these things very well. And that is simply just a combination of this guy, the horizontal motion that we have defined earlier, and this new guy, the vertical motion. So we combination of these two. So in this situation, you are throwing up and down. In this situation, you are going right and left. But when you look at the projectile motion, you realize that it is about, the ball is going up, at the same time it's going to the what? Right. It's going to the right, at the same time it is coming down. So it's a combination of both. And so therefore, we have the component of its velocity in the x direction. That is going to be u cosine theta. And this is going to be u sine theta. So having done that now, let's now begin to analyze each of these things one after the other. So the components of this now, based on the equation of motions that we have, we're going to be using most of the vertical component of this motion because, as you can see, this body is proceeding up. So if we start with the part that we have v equals u, so I told you when it is going up, it will be v equals u minus gt. So let's do something here. You'd realize that if this body is starting from this place, the initial velocity is going to be the vertical component of this. And then if it reaches this point, it is the point of maximum height, like I've explained earlier, because if it reaches that point, it begins to descend again. So if that is the case, then that implies that the final velocity at this point, at the maximum point, is going to be equal to 0. So if I apply that to this equation, that implies that v, which is the final velocity, becomes 0, and u is going to be u sine theta, and this will be minus gt. And so what will this time represent? It is the time taken to reach the maximum height. So let's call that t subscript h. If I solve for t subscript h here, this implies that gth equals u sine theta. And that implies that th equals u sine theta divided by g. So this is the time it takes a projectile to reach its maximum height. And one thing about projectile is that it is symmetry in nature. It is symmetrical in nature, kind of. Although there are exceptions, but like for so many cases, it is symmetrical. Like for instance, the time it took for it to go from down here to this up part is the same time it will take to go from this up here to the same level at the down here. So that implies that if I want to get the total time it takes for it to move from this point to this point, it's going to be double of this. It's going to be double of this. And that time actually has what we call it. We call it the time of flight. We call it the time of flight. What is time of flight? Time of flight is simply the time it takes a launched projectile to return back to its plane of projection. That is, you launch it from here, it moved, and it returned back to the plane of projection. The time it took to achieve that is what we call time of flight. And this time of flight, we can solve for it in another way, apart from the one I just described now. We can solve for it in another way because we know the initial velocity with which it is moving, and then we know the height that it has covered. Because if somebody starts from level 1, that is the plane of projection, they move to level 2, they move to level 3. But again, they came back down and come back to level 1. How much height would you say they have covered? They started from level 1 to level 1. They have not covered any height actually. You remember the concept of displacement and total distance covered. That's exactly, it's more like displacement now. So their height, don't forget I said height is replacing displacement. So if you start at level 1 and you come back to level 1, that means that your height is going to be equal to 0. Your height is going to be equal to 0. So in this situation, if the body is moving from the plane of projection and is returning back to the plane of projection, the time it took will be the time of flight. The height at that point is going to be 0. So using h equals ut minus half gt squared. So h in this case is going to be 0. U in this case is going to be the vertical component because we are still considering it moving through that place. So that's going to be u sine theta minus half gt squared. So permit me to write this t as capital T now, being the time of flight. So if you solve for t here, you have half gt squared equals u sine theta, and what that implies is that there's another t here, so u sine theta multiplied by t. So in that situation, I'm going to have to double back a little bit here, so I omitted the t. So we have 0 equals u sine theta multiplied by t. So in this case, you still have t as the time of flight. So if you solve this now, you have t can be factorized out, t multiplied by u sine theta minus half gt. And if that is the case, that implies that t is either equal to 0 or u sine theta minus half gt equals 0. Whenever two things are being multiplied in math, it implies that either one of them will be equal to 0. And it makes sense that t should be 0 because the body is going to be at this level at 2 times. The number 1 time is when the body has not been launched yet, and that is why we have time 0. The other time is when it has gone up and returned back to the plane of projection, and that is the time we're going to be solving for here. So in this place, that implies that half gt is going to be equal to u sine theta, and that implies that t, so that will be 2u sine theta all divided by g. So you can see that this is the double of this guy. So the time it takes to go up and come down is double the time it takes to go up. So that implies that whatever time it took to get here is the same time it will take to also come down as well. So time taken to reach maximum height is half of total time of flight, and that is time of flight. Now let's now talk about the maximum height it will reach. Now we've been given that h equals ut minus half gt squared, and I told you already that if it's going to reach maximum height, we also have v squared equals u squared minus 2gh. So let's see which one we're going to use here. I think this one will be the best one to use. We had said that if it's going to reach maximum height, v at that point is going to be 0. So this will be 0 squared. We're still using u sine theta all squared minus 2g. So permit me to use maximum height as capital H here. So that implies that 2gh equals u squared sine squared theta. So sine squared theta means that you find the sine theta, then you square it. That's what it means. It doesn't mean that you square the angle before you now find the sine. So if you solve for h here, h would then be u squared sine squared theta all divided by 2g. And this is what you use to calculate the maximum height reached by a projectile launch. The next one is what we call the horizontal range. The horizontal range R. Now, this one is actually in the horizontal direction. So permit me to pause a little bit and do a little bit of analysis. So for a body that is in projectile motion at its launch, like I said, it has two components of motion. There is the vertical and there is the horizontal. You see, in terms of the vertical, like I've explained, it starts with an initial speed, and when it gets here, its final velocity is going to be equal to 0. But here's the thing. Final velocity in the vertical direction is going to be equal to 0. But this guy actually, it possesses both horizontal and vertical component of velocity. It possesses both horizontal and vertical. Horizontal and vertical. So what happened is that the horizontal component of the velocity is not changing. So ux is constant and not changing. That is why the body is not accelerating in the horizontal direction. The body is not accelerating in the horizontal direction. Take note of that. So the only place where acceleration is taking place is in the vertical direction. So we now want to calculate the distance covered from this point to this point. That is this horizontal distance. This is actually what is regarded to as the range covered. This is what is regarded to as the range covered. So we want to calculate this distance. How do we do it? Since it is horizontal distance, we have to use the horizontal component of the velocity. And since it is not changing, then we can use that S equals Vt. In this situation, we are going to be using R as our range, and we're going to be using Ux multiplied by T. Now, so what will the T be? Since I'm covering distance from this point to this point, what that means is that the time taken is actually the time of flight. So that implies that this will be R equals Ux multiplied by big T. So range is then Ux is U cosine theta. What's time of flight? Time of flight, we got it as 2U sine theta, everything divided by G. We had gotten that earlier. So now R will now be 2U squared sine theta cos theta divided by G. And that implies that R equals U squared multiplied by 2 sine theta cosine theta, everything divided by G. So the thing is that in trigonometry, this 2 sine theta cos theta can actually be rewritten as sine 2 theta. So therefore, the range of a projectile motion is given as U squared sine 2 theta, everything divided by G. Now, what does 2 theta mean? It means you multiply the theta by 2 first, then you now find the sine of that angle. Unlike sine squared theta, you find the sine of the angle, then you square it. So this is the formula for the range of a projectile motion. And these are the major components of the projectile motion. Take note of every important detail I've put up right here. So there's a special case that I want to discuss, and that will be the last part of this particular class, is if you have a platform. So let's say you have a platform and you want to launch a projectile from this platform. You want to launch a projectile from this platform. We call it launching it horizontally. So what happened is that, you notice that as the object begins to move, it shoots out at first, but it cannot continue to move horizontally. At a point, it begins to bend, it begins to curve, and it curves downward. It curves downward, and it makes it to the ground. What if I told you that the time it takes for this object to cover this path and get down is also the same time it will take if you had thrown the object right here and it moved down, straight downward here. So you throw an object horizontally and you throw it like this, it's going to take the same time for them to reach the ground. So as usual, there is horizontal component, which is the Ux, and there is the vertical component. But since this guy was initially launched at he was launched horizontally. When something is purely horizontal, then the vertical component is going to be 0. So initially, the vertical component of this guy is 0. But as it begins to go down, it gains uy. it gains uy, it gains uy. So its velocity in the vertical component is increasing. But what happened to ux? Like I've explained, ux remains constant. Ux remains constant. The horizontal part remains constant. So now, like I've said, the same time it takes this, so to fall down this height, is the same time it will take this as well to go through this point and come down here. So we can now use something about that. Since we know that h equals ut, as you're going down, that will be plus half gt squared. And since I'm dealing with the y component, the initial velocity for the y component is 0. So this part becomes 0. And what does that imply? H equals half gt squared. But for this other guy as well, the same thing as well. It will take the same time for it to cover. So let's call this distance, let's call it a distance x. So the same time it takes to fall through this height is the same time it will take to cover this. But you know, this is the horizontal component, and since the horizontal component is constant, so that means that s equals what? Ux multiplied by t. Now, you know that these two t's, they are the same thing. They are the same thing. So what happened then? I can easily substitute this into this equation. So what I'm going to have now is that x equals ux multiplied by t. So that implies that I can easily substitute this down. So in this place, I can actually solve for t. So this implies that 2h equals gt squared. And t is going to be square root of 2h over g. So therefore, x is going to be equal to ux multiplied by, what is t now? Square root of 2h over g. So this is what you use whenever you launch a projectile horizontally from a certain level. Whenever you launch a projectile horizontally from a certain level. I know that I try to combine a lot of things in this particular one video. So what you need to do is that you need to watch the video over and over and over again. And if you have any part that is confusing, you can just let me know in the comments and I'm going to respond to you. By the way, if you have not subscribed to the channel, you should right now. You should right away, and check the previous classes as well. Some of these previous classes will help you understand this one better. Just check the playlist. You see what we are talking about there. And that's it for today. Don't forget to like, share, and subscribe. I'll see you in the next one.